Two is the boy, is your boy, is your is your boy. Whoa, it's not even streaming at the point? I'm not even live at this point? What? Because I'm not seeing it on YouTube. I am not seeing the live on YouTube. What's going on? What happened here? This is not normal. Yep, now it's on. Fuck, how is it? Oh, okay. At least now I can see the live stream is going on. Josh, why do you care about this? I don't know. I don't know. Like the title is said, Thermodynamics summit. What? Thermodynamics summit. What? Thermodynamics summit. Whoa. Did I say some profound knowledge? Did I just give you some wisdom? Yeah, I did. Thermodynamics summit. Thermodynamics summit. Yeah. Did you get what I mean? Thermodynamics summit. Yeah. You are an intelligent one, not gonna lie. Yeah. If you understand what I say by thermodynamics, you just made it. Don't listen to others, you just made it. Don't tell me it's again on the same page. Mm-hmm. $15. Huh. So I have to start with the isothermal. So in most cases you could say enthalpy is internal energy. Nope. 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 Isothermal, constant T. The heat produced or heat absorbed is equal to work produced or absorbed. Work on or by the system is not equal to 0. Delta U, delta H equal to 0. Gas slowly expanding in a piston. Really? In a piston, gas is slowly expanding? Slowly? I don't know, bro. I don't know how piston works. Isobaric constant P. Heat produced is the change in enthalpy. Work is P delta V. Delta U not equal to 0, delta H equal to 0. So enthalpy is the heat produced for isobaric where pressure is constant. Heating water in an open container at atmospheric pressure. Isochoric. Volume is the constant when temperature equals change in internal energy. Or heat produced or heat equals change in internal energy. Work 0. Because there's no physical change. Internal energy equals heat, which is not equal to delta H. Wait. Delta H or enthalpy, change in enthalpy is not equal to heat. And internal energy is also actually change in internal energy is equal to heat. Okay. Rapid compression and expansion in an insulated piston. Rapid compression and expansion in an insulated piston. What does an insulated piston mean? Insulated means no temperature going across the surrounding system. Is that what you mean? Yeah. Temperature is 0. No, heat is 0. Heat is 0, not constant temperature. Why each behaves this way? Isothermal internal energy depends on the temperature. So heat exchange equals work done. Isobaric system can expand. Heat goes into increasing internal energy, doing expansion work. At constant pressure, heat equals enthalpy change. Isochoric, no expansion possible, no work, all heat changes, internal energy. Adiabatic, no heat exchange with the surroundings. That's what Q equals 0 means, okay. Any work comes from internal energy, expansion means temperature drops. Expansion means temperature drop. PV equal to nRT. Expansion means V increases. So if V increases, P decreases. If you want to compress this into a memorization sheet, ultra short exam version. Nope, I don't want that. I'm gonna start with the table. Process type. Eight minutes. Come on. Go. Isothermal. Constant. Heat. W. Work. Or heat is also the same, right? Delta U. Change in, wait, change in internal energy. Yep. Delta H. What is delta H? Fuck. What is delta H? It was change in enthalpy. Fuck. Change in enthalpy. Enthalpy, there's a H. What else, brother? Example. Yeah, example is important. Isothermal, isochoric, isobaric, okay. Isochoric and adiabatic. Isothermal constant T. Tempa. So heat and work is equal, right? Yep. Internal energy. What the f is internal energy? It's gonna be 0. But delta H is not gonna be 0. It's also gonna be 0. I gotta write this. Does not mean they are equal. I did not change the camera position, right? I know. I know, brother. Don't worry. Got you, fam. Oh, got you. You guys ready for the best transition out there? A 3, 2, 1. Okay, did that work? Oh, okay, there we go. There we go. That worked. Not gonna lie, doing push-ups, my chest is starting to feel. Oh, it feels. Starting to feel. What's the word? Hard. Hardcore. Example. What the fuck is example? Gas expand slowly in piston at constant temperature. That's not a good example, though. I'll write that example. I'll look for another better example. Isobaric. Constant pressure. Yep. Atmospheric pressure, of course. It's annoying. Pressure. When it's constant pressure, H equals PV, right? What the fuck did I just say right now? Q is delta H. So heat is changed in enthalpy now here. Change in enthalpy, work. What about work? Works P delta V? P delta V. Change in internal energy. It's like normal. Q plus. Yeah, normal. Q plus W. Or delta H plus P delta V. I gotta have a distinct separation. Equals, what was it? Q, heat. Example, boiling pot in atmospheric temperature, right? Heating water in open container. I gotta separate the examples too. Heating water in open container at atmospheric pressure. You know what? I gotta do a small editing. You come here, bro. Got him. Got that bitch. Isochoric, what does that mean? Constant volume. What does that do for heat? Heat not equal to 0? Work is 0. I know work is 0. Oh, isochloric. Ah, heat is change in internal energy. Oh, okay. 15 minutes. Push-up time, I guess. And work 0. 0. 0. Internal energy. Change in internal energy is basically heat, but enthalpy is not equal to 0. Okay, it's not equal to Q. That's the only point you can make. That's the only point. Wait. Think stupid. I guess. No, there should be something else. Like that's too obvious. It's not equal to Q. Delta H push-ups. I forgot to do push-ups. I gotta keep that open because I feel like there's something better. Gas heated in rigid steel bomb calorimeter. Gas heated in rigid heat bomb calorimeter. Ow. Adiabatic is where what was the point? Heat was 0, right? Yep. Heat equals 0. That's interesting form of system. 0. Work PV not equal to 0. Yeah, that's PV, bro. That's PV, bro. P delta V. Internal energy is negative work. Minus W. But delta H is again not equal to 0. I mean, that's so obvious. Rapid compression and expansion in an insulated piston. Compression and expansion in an insulated piston. Push-ups. $15. 'In isochoric, four. What? Then just isothermal example. What actually makes it isothermal? Gas in the piston with a heat pad. A gas inside a cylinder with a movable piston. The cylinder is placed in contact with a large head reservoir water bath at fixed temperature. You slowly expand the gas. What physically happens? Gas tries to cool when it expands, but heat flows in from the reservoir at the same time, so temperature stays constant. Why? This is truly isothermal. Heat in, work out, energy doesn't accumulate as temperature change. Isothermal is not just constant T by definition, it requires low heat exchange with surroundings to maintain T. So, isochoric, why delta H not equal to 0, start from definition, delta H equals delta U plus delta PV. In isochoric process, V equals constant, W equals 0, delta U equals Q. Internal energy equals heat. So Q plus V delta P, why this matters. At constant volume, enthalpy change includes both heat added to the added and the change in pressure contribution. So V delta V. V delta P, okay. So that's the more precise answer. So it's Q plus V delta P. V delta P. Adiabatic, more specific meaning of delta H, not just not equal to 0. Start conditions Q equals 0, so delta U equals minus W. Now in enthalpy, delta U plus minus W plus delta PV. Okay. My equal to is not good. Equal to Q plus V delta P minus W plus delta PV. I gotta write delta H equals delta U plus delta PV. Delta U equals Q plus W. Or minus 0, don't matter. Who the fuck started this though? I still haven't written the example. So, can I get a better articulated example for isothermal? Yeah, I gotta make it. What does eher mean? Eher. It's like it's like a formal version of. Oh, I forgot it does not work. A gas trapped in a cylinder with movable piston. Sentence. A single sentence. One line example. An isothermal process occurs when a gas expands and. I need a one sentence example. Like the example you said was correct. Correct. I just need that example in a way that if I had to present this, I would be able to explain it. A gas expands slowly in a piston. Oh, bro, that's too much words. Gas expanding slowly in a piston that is kept in contact with the in a piston that is kept in contact with a large heat bath. So with a large heat bath. So heat flows. Exact heat flows. So heat flows to maintain constant temperature. Okay. Okay, I feel like this is good enough for its part B. Why does it often make sense to use enthalpy to describe thermodynamic process of chemical reactions? Because enthalpy, 15 minutes? Fuck. 15 minutes to push it, right? Fuck. But before that, I'll be right back. The beauty of the world, Savannah. Push-ups. Ah, 60, somewhere around 60. It makes sense to use enthalpy because most chemical reaction occurs at constant pressure, and under this condition the heat exchange with the surrounding equals the enthalpy change, making enthalpy a direct measure of heat of reaction without needing to account separately for expansion work. 15 minutes. Fuck. Wow, that looks fucking amazing. Yep, that looks amazing. can explain a bit more, because I know that a reaction is dependent on state functions than a path function, and enthalpy usually accounts for path function, so it's better to go with that. This is a sort of reasoning that I used for myself. Could you explain a bit more? Ranudas, why I ended up here. A lot of people ask that question, you know. A lot of people ask themselves, "Whoa, why did I get? Why am I here? I could be anywhere else, but I'm here." It's a valid question, you know. What's up, Ranudas? How you doing? Is it your first time checking out this stream? Because I feel like I haven't seen your name before. Am I right or am I wrong? Or yeah, of course. I'm guessing that's the answer to the question. It's your first time, right? Bring it in. Bring it in. Bring it in. Welcome. Everyone's welcome here. Well, what made you click on the stream though? Was it the thermodynamics? Was it the PERFOMAXXIN? Was it the day 310? What made you click? I don't know if I'm asking too many questions, okay? I'm someone who asks too many questions. Apologies. Your reasoning about state versus path function is heading in the right direction, but the key point is key point here is simpler and more practical. Why enthalpy is used for reactions. Most chemical reactions happen in open system. Beakers, flask, biological system. Pressure is essentially constant. Constant pressure. What was the case? Isobaric? Yup. Isobaric. Also, Ranu, where is it? Ranudas, apologies for the latency. There's like a 20-second delay, right? That's just YouTube. Oh, okay. So, PERFOMAXXIN, that was the term that made you click. Interesting. That's cool. So basically, I just want to give you an idea on what I'm doing. I stream whenever I study. That's it. And I do other random stuff on the channel, of course, because I'm a human being. But basically, it's just I record myself studying so I can track my studies. And I gotta say, I'm not someone who is really good at studying. That's why I had to take this measure. I wish I was someone who was really good at studies. But yeah. Fuck. And PERFOMAXXIN is basically me trying to get shit under control. Most chemical reaction happens in open system. I read that. What problem would we have if we used internal energy? In reactions at constant pressure, part of the heat goes into expansion work, so the measured heat is not equal to delta U. That makes internal energy less convenient experimentally. What? Why enthalpy solves this? Enthalpy is defined as U plus PV. So delta H equals delta U plus P delta V. That's... Yo, I appreciate that, brother. Run or sister Ranudas. That means a lot. Appreciate you for checking out the stream. Respect. What this means physically: heat released or absorbed in a reaction at constant pressure is directly measured as delta H. P delta V. I'm still confused on the part where... Again, I feel like I have already asked you this, but I'm confused on the part where work is also pressure volume dependent, and we are redoing it again when it comes to enthalpy. What's up with that? Huh? What's up with that? Ow. Start from the correct meaning of work. In chemistry, work, PV work only, W equals P delta V. So the first law becomes Q minus P delta V, or Q plus P delta V, yeah. Rearrange, Q equals delta U plus P delta V. Now look at the enthalpy definition. H equals U plus P delta V. Take the changes. So, at constant pressure, so delta, so key insight, but this removes your confusion. Compare both these expressions. Q equals delta U from enthalpy, so delta H equals QP. So we're doing PV twice? No. Okay. So we're just rearranging. So enthalpy is more related to heat than... So enthalpy is more related to heat than internal energy. $15. Not gonna lie, I'm not gonna do the push-ups right now. Oh, fuck. I'm kinda tired. The timer, it's gone. Okay. 5 minutes. Just let me do one thing within these 5 minutes. Is the 5 minutes timer up? No. But only in specific sense. I'm gonna cancel the timer. 15 minutes. Fundamental energy stored in the system includes microscopic motion and interactions not directly measurable as heat, enthalpy, but not more heat but more directly linked to heat exchange in real condition. Enthalpy is not heat itself, it's a state function that equals heat under constant pressure condition, so it is a convenient way to describe heat effects on reactions in open system. Yes, at constant pressure, okay. One line exam answer. Enthalpy is more closely related to heat than internal energy because at constant pressure, enthalpy change equals the heat exchange with the surroundings, making it useful for describing chemical reaction. While is chemical reaction mostly involved with heat? Okay, kind of makes sense. Okay. Okay, this kind of makes sense. But is heat the best to describe heat the best function, state function to describe chemical reaction? No, heat is not a state function. It's actually a bad choice to describe reactions in general. Why heat is not suitable? Heat is path function, not the state function, meaning it depends on how the reaction happens, not only an initial and final state. Same reaction, different heat depending on the route, making it unreliable. Why enthalpy is better? Enthalpy is a state function. Under constant pressure, heat and enthalpy is same. Okay. Okay. Quantity, state function, depends on path. Yes, good for reactions. No. Internal energy sometimes. Enthalpy is the best. Core conclusion. Heat is not suitable to describe a chemical reaction because it depends on the process path, while enthalpy is a state function that gives a unique value for reaction under constant pressure conditions. But if it's a constant pressure condition, then here, if it's a constant pressure condition, that means if it's in a constant pressure condition, then that means what? Then that means enthalpy is heat. So I was saying if heat stat enthalpy acts, if enthalpy state function under heat, under constant pressure, it's same value as heat path function. But when pressure is constant, then the heat is also a state function. You're mixing two different ideas, becomes equal and becomes a state function. What actually true for constant pressure? This means numerical value of the heat equals enthalpy change, but heat is still a path function, enthalpy is still a state function. The key mistake in your constant pressure does not change the nature of heat. It only creates a special case where heat transfer equals to delta H, but heat still depends on how the process is carried. So, enthalpy is a state function that accounts for both heat and internal energy. Could you explain what makes First correction, enthalpy is not heat plus internal energy. Correct definition, H equals U plus PV. So it is internal energy plus a term for expansion work against pressure. It is internal energy plus a term for expansion work against pressure. Enthalpy is not heat plus internal energy. Enthalpy is not heat plus internal energy. I gotta look into GCNR. Fuck. Let me first complete this. Yep. First correction, enthalpy is not heat plus internal energy. So internal energy plus a term for expansion work against pressure. What enthalpy actually does, start with the first law. Most chemical reaction PV work only, so Q equals delta U plus P delta V. Now define H equals U plus PV, delta H equals delta U plus PV. So at constant pressure, only at constant pressure, matches real lab conditions. Most reactions happen in open beakers, flask, biological system. These are constant pressure systems. So enthalpy directly measures measured heat. Enthalpy directly equals measured heat, removes work complement. What was that? Okay. "15 minutes. Why Delphi is better for reaction? I get the part where it's constant pressure is good. Removes work complication, gas expand or contract. And Delphi bundles this into one quantity. State function advantage, you depend on microscopic energy. H depends only on the initial and final state, so same reaction, same delta H, no matter the path. Simple physical picture. Think of a reaction using internal energy. Energy goes into heating molecules, pushing the atmosphere. Work using enthalpy, both internal energy changes and cost of pushing surroundings out, so nothing is left out at constant pressure. Enthalpy is better for chemical reaction because at constant pressure it directly equals the heat exchange and automatically includes both internal energy changes and expansion work in a single state function. I don't know, I feel like I need to go deeper into this. I could right now I'm just gonna write that, but I'm not convinced. And I don't have time to just right now just go deeper. Enthalpy is better for chemical reaction because at chemical reactions because at constant pressure it directly equals the heat exchange. It directly equals to the heat exchanged. And automatically includes both internal energy changes and expansion work in a single state function, and automatically includes both internal energy changes and expansion work in a single state function. Work in a single state function. I need to know. I'll look at it later. Define standard enthalpy of formation and standard reaction enthalpy. I know this. So basically, standard enthalpy of formation is the change in enthalpy when change in enthalpy or change in energy when or energy required for a molecule to form from its elemental form. Give short explanation on the Hess law. Why is it allowed to freely rearrange these reaction equations to obtain reaction enthalpy? The enthalpy change when 1 mole of compound is formed from its element in their standard states under normal standard conditions, usually 1 bar. Standard enthalpy. Oh fuck! I forget the H of formation. Delta FH0 Standard reaction enthalpy. Reaction enthalpy, that's it. Enthalpy change when one mole of a compound is formed from its elements in their standard states under standard condition. The enthalpy change for 1 mole of a compound to form from its elements, not elemental. The fuck is this? In standard conditions. Conditions in standard states. States and conditions. One bar, 298 Kelvin. Enthalpy change when a reaction occurs as written in a balanced chemical equation with all the substances in their standard states. Enthalpy change when a reaction occurs as written in the chemical equation. The enthalpy change when a reaction occur as written in a balanced chemical equation. With all the substance in their standard states. With all the substance in their standard states. I should make sure my handwriting is better. It's still not equation. It's not proper. Key points applies to chemical reaction. Depends on stoichiometric coefficient. Can involve multiple substances. Always refers to 1 mole of product. I think that's it. Can I do this where no, I can't do that. Okay, that's good. That's good. Whoa, the camera just stopped working? No, not this. The older one. It was from here, right? Yeah, it was from here. I missed it. Where's that part? Gas changer was here. This is hard. Shit is hard. So till here. Around till here. Oh, there we go. I gotta check it. Screw tight thermos. That was the part. Fuck. So that means I'm already there. So screw tight thermos and planet Earth. That's the planet Earth. So what should I do? I gotta have my name. Hess law. 15 minutes, okay. If I understand, why is it okay to rearrange, change the enthalpy of a reaction? Because enthalpies are state functions, so it only depends on the initial and final state of a reaction, so it should be reversible, right? Hetz's law states that total enthalpy change of a reaction depends only on the initial and final states, not on the path taken. Yeah, basically. Total enthalpy of a reaction. Enthalpy change. Okay. Why is it looking? It looks like that. Change of a reaction. Depends only on the initial and final states, not on the path taken. Now, what was the reason why reaction equations can be rearranged? That's not part B, but okay. It is allowed because enthalpy is a state function, meaning from that Hess law is valid because Hess law is valid because so delta reaction enthalpy of reaction change in enthalpy of reaction change in reaction enthalpy depends only on the initial and final states, allowing reactions to be algebraically rearranged without changing the overall enthalpy change. Thus allowing reactions to be algebraically rearranged without changing the overall enthalpy change. Balance the reaction equation given below. C3H6, that's a propene, right? Yeah, propene. Plus O2 gas. Burning a propene gives CO2, of course. H2O. What is happening with my screen? Like it's dimming. It dims, it brightens, it dims, it brightens, dims, brightens. So we got 3 carbon. We need 3 carbon here. If I put 3 here, it's going to lead to 6 oxygen. So we got 6 plus 1, 7 oxygen. And we have only 2 oxygen on the left. We got 6 fucking hydrogen. So we need 3 hydrogen. We need to put 3 here, so it's gonna be 6. It's gonna be 6 plus 3, 9 oxygen. So we need 4.5. That is 9 by 2. Right. 9 by 2. 3. 3. If I understand. No. Wait, 6 oxygen. 6 plus 3, 9. Yeah. As the balanced, use the reaction equations and reaction enthalpy in the table below to calculate the reaction enthalpy when burning 1 mole of propene. Okay. That's propene, right? Yeah. Propene plus 1 H2 gas, C3H8. Okay. C3H8 plus 5 O2 gives 3 CO2 plus 2 H2O. Two H2O gives 2 H2 gas plus 1 O2 gas. Why did I fucking write 1? Am I stupid? Are you stupid, boy? Yes. I'm stupid. Fuck, man. Shit's fucking ridiculous, brother. It's fucking kilojoule per mole. 124 minus 2220, 572. So if I understand, the first 2 cases, energy is released. The third case is where energy is absorbed. Yeah, if you want to split water to fucking hydrogen gas and oxygen gas, you gotta spend some energy. Yup, I agree. So combining reaction 1, 1 and 2. C3H6 gas. Fuck, I hate rewriting it. Gives C3H8 gas. C3H8 gas plus 5O2 gives 3CO2 gas plus 4H2O. Cancel, cancel. Minus 124 plus minus 2220. Fuck, do it! 2000 minus 2344 kilojoules per mole. Reverse reaction 3 and combine with equation 1. Equation, it's not math, but yeah. C3H6 plus, I don't know, H2 gas plus 5O2 gives 3CO2 plus 4H2O. 2H 2H2 gas plus O2 gives 2H2O. How do you cancel it though? It's gonna be 2. It's gonna be 1. It's gonna be 4. It's not looking good. So, fuck. So we get 1 H2O, right? No. We get 1 H2O and... Fuck, that's not good. That's not looking good. I've did this problem before. Come on, it's not the first time I'm doing this. It's combined. It's not cancel. Yeah. Idiot. Yup. Apologies, gang. So, combine. So after combining, 3 3 Fuck. 3H2. 3H2 plus 6O2. What does that mean? That means 3H2O plus 3O2. No, it does not mean 3O2. 6O2 means how many? That means 12. We're only taking 3 from that, right? So we got 9. Again, for 9 by 2, O2. Three CO2 plus 6H2O, 3H2O. And the math. So delta RH1 plus minus delta RH3, which is like, come on, minus 2344, minus 572. Can I do this math? I can, but I don't wanna. I don't wanna. 2, 3, 4, 4 minus. No, adding. Oh, if it's adding. Plus 572. 2,916 kilojoules per mole minus. It's a lot of energy to be released. One combustion or burning of 1 mole of propene gives 2,916 kilojoules, bro. That's a lot of energy. It's a lot of energy. A bomb calorimeter. Okay, before you start answering this, you gotta let me know the formulas. Okay, before you start answering this, let me know the formulas and the meaning of the terms involved. Yo. Where are the timers, brother? Where are the timers, brother? Let me see. How long is the stream going? It's going for, fuck, 2 hours. You kidding me? 2 hours? Like 2 hours? 1 plus 1 hour? Like 2 hours? Whoa, that's fucking crazy. That's some crazy stuff, okay? That's really crazy. It's crazy. Electrical energy supplied. Heat equals UIT. U. Electrical. Oh, okay, okay. Why are we going for log? Why is it log? What's the log? In. Oh, okay. In. Okay, it's not log. Electrical energy supplied, voltage, energy per unit charge, pushing electrons, rate of charge flow, duration of energy input. This equation gives total electrical energy converted into heat. Voltage, current, time. Okay, so that's for caloric. No, that's for electrical energy supplied. Calorimeter constant with energy supplied by change in time, change in temperature. Change in time? That's the first time I'm hearing that. Oh, imagine equations with change in time. Yeah, there are equations, I believe. Five minutes. I need to customize a little bit of my channel. Just a little bit. Just a little bit. 19 minutes and 30 seconds. So we're gonna use seconds, right? We should go for seconds. Okay. Mm-hmm. Phew. I feel like my neck is fucked up. Oh, not gonna lie, that kind of reset the fucking neck. Here, what's the usual unit of time used? Seconds? Okay. Electrical energy supplied. You know what? I need to check one thing. Gas change. That was the next part. You know what? Let me check one more thing. No, just go close, bro. Can I overwrite it? Like, if I want to write something here. Yep, that's all I want. That's all I need. That's all I need, bro. I'm starting to get hungry. And I should eat. I should like this, right? 8 calorimetry. A bomb calorimeter, energy supply, electrical energy supplied formula. U, is it U? Q. U, I, T. U equals voltage. I equals current. T equals time. Seconds, ampere, volt. Joules. Oh fuck! I'm just gonna write it. 6 into 3 into 19 minutes 30 seconds equals 1171.17 into 10 raised to 3. Nine into 1.17. 10.53. 10.53 kilojoules. Calorimetric constant. C cal. Q by delta T. Energy energy supplied delta T change in temp 25.7. .7 Kelvin. So now it's going to be 10.53 by 2.7. 3.9. 3.9 kilojoule per Kelvin. That's the calorimetric constant. Joule per Kelvin, kilojoule per Kelvin, yeah. In a bomb calorimeter, electrical energy supplied equals in a bomb sample weighing 0.9 grams with the following formula. Is burned with oxygen to produce CO2 and H2O, resulting in temperature increase from 22. Determine the heat of combustion. Heat the combustion of glucose, temperature change. Use calorimeter constant 7.8? I don't think so. I got 3.9. Heat absorbed by calorimeter. You know what? I should probably write it as joule per Kelvin. B. Heat absorbed by the calorimeter, Q equals C calorimeter into change in temperature. Oh, that was the link. Where is it? Calculate standard Delphi formation of the compound given. Okay, it's kind of, not gonna lie, these questions are kind of easy compared to, says, fifth semester. No timers? Fuck. I feel like I'm getting distracted again. Again! So, what are you doing? Using the calorimetric constant. Use the heat absorbed by calorimeter, the formula where, yeah, I got it. And you get heat absorbed or energy. This is the heat absorbed by calorimeter, so reaction released. So reaction released it, moles of glucose, molar mass, number of moles. Okay, heat to combustion per mole. So heat to combustion per mole is uh, heat released as part of the reaction divided by the number of moles. Okay. Calculate the standard Adelphi formation of the compound given. Why is it allowed in this specific case to equate heat and Adelphi? Pressure is same. I know this. Motherfucker. I believe it's because pressure is same because it's a bomb fucking calorimeter, pressure and volume. Whoa, wait. Is pressure the same though? But I'm missing one. The reaction equation of the compound you're finding is not shown in your message. Okay, I'll paste the whole question, bro. Use as well with the combustion reaction. Use reaction Adelphi for B. Apply formation Adelphi reaction relation. Adelphi reaction of formation of glucose. Oh, I gotta know the formula? They did not give me the formula? Nope. I mean, I could formulate because we know, yeah. Use reaction Adelphi from B. Apply formation Adelphi relation. Calculate products. Now the last part. Why is it allowed in this specific case to equate? Which part is this talking about? Which part it refers to the bomb calorimetric combustion experiment in parts A and B, not part C. The specific case means the combustion of glucose in a calorimeter. Heat equals in Adelphi here, constant volume, no expansion of the system volume. So change in Adelphi is heat. Wait, it's this one is internal energy. It's not Adelphi though. But this. Why they still say Adelphi for combustion reaction we usually won't, because reactions are defined at constant pressure, but for ideal gases in this case correction is small, handled separately in standard tables. So the question they want you to say, even though the bomb calorimeter measures heat at constant volume for combustion under standard conditions, the difference between internal energy change and Adelphi change is accounted for or small. So heat is taken as equal to Adelphi change. Is pressure equal though? Is pressure constant? That's what I want to know. I feel like no, because the when reaction happens, yeah, gas is gonna expand and pressure is gonna change. Am I am I getting stupid maybe? Fuck. Okay, I feel like I should eat something because my what's it called? Attention span is fucked up. He's not fucked up right now. Say that, bro. Fuck. It's new one, right? How long was the stream going? 2 hours, 30 minutes. You know what? I'm gonna end the stream. I'm gonna eat something. Peace. Peace out, YouTube.